Hello everyone, welcome to my YouTube channel SGKmistry Lectures. In this video, I'll be explaining organic transformations and reagents in detail, and the topics that will be covered in this video are, first of all, we'll be discussing on functional group interconversion, which includes detailed explanation on oxidation and reduction reactions. So we will be talking about the oxidation and reduction reactions of the important organic compounds like aldehydes, carboxylic acids, ketones, etc. And also, I'll be explaining in detail about the common catalysts and reagents, which includes organic, inorganic, organometallic, as well as enzymatic reagents that are included in this, along with the different types of catalysts. And specifically, we'll also be covering on chemo, regio, as well as stereoselective transformations. We'll be learning more in detail about these different types of transformations, that is chemoselective, regioselective, and stereoselective transformations with suitable examples and explanation for each of them. Along with this, we will be also learning about important reactions such as Shapiro reaction, Chichibabin reaction, and Stark-enamine reaction. So let us start with understanding about oxidation. So first of all, we know that oxidation of an organic compound, when I'm considering, it is nothing but it is the addition of oxygen or removal of hydrogen, or we can also, in terms of electrons, we can say that it is the removal of electrons from the organic compound. So simple examples, I can write it in the terms of general equations. So for aldehydes on oxidation will give carboxylic acids, RCOOH. Here oxygen is added, one more oxygen is added. So from RCHO, you're going to get RCOOH. Similarly, if you're taking alcohols, so again, if I remove hydrogens, so it is nothing but oxidation is addition of oxygen or removal of hydrogen, right? So if I remove two hydrogens here, then what I'm going to get? I'm going to get RCHO. So the primary alcohol here, in this case, I have taken the primary alcohol. This is primary alcohol. So the primary alcohol on oxidation, that is by the removal of two hydrogens, you're going to get the aldehyde. So primary alcohols are oxidized to aldehyde. Let us talk about phenoxide ion. So this on oxidation in the presence of cerium 4 plus ion, you get C6H5O dot. That is, here one electron is removed. So from the anion, you're going to get the free radical because of the removal of one of the electrons, right? So next, coming on to oxidation of hydrocarbons in detail. So first, let us look into oxidation of alkenes. Under oxidation of hydrocarbons, first let us see how the alkenes undergo oxidation. So first method is by epoxidation. So olefinic double bonds, they react with peracids to give the epoxides. So epoxidation is also a type of oxidation where oxygen is added to the double bond, across the double bond of the alkenes. So mainly here, the double bonds, whenever the double bonds are present in the alkenes. So first of all, we know that alkenes have double bonds in them, CC double bonds. So these double bonds, they react in the presence of peracids. They form epoxides. So metachloroperbenzoic acid, okay, so this particular reagent is the most useful reagent for effecting this alkene epoxidation oxidation, right? So let us see the general reaction. So let us take the alkene. So C double bond C, I'm just taking the general equation. So now, if I'm going to treat it with ArCOOH. So here we have the perbenzoic acid, right? So here in this case, we have taken in the common reagent that is used is metachloroperbenzoic acid. Here I'm just taking the aromatic ring, which is again having the perbenzoic acid group. So now this double bond, here we know that there is alkene, right? Or the olefine. So let me write it clearly. So here we have alkene. So this alkene on reaction with here you can see there is perbenzoic acid along with, say, aromatic ring can be anything. There can be substitutions also. So here epoxidation takes place. So where there was a double bond, there you can see the addition of oxygen has taken place, and because of which you get an epoxide. So the other groups remain the same. Along with that, now since one oxygen has been used from this particular reagent to, to add to the double bond, so that to form the epoxide, you're going to get ArCOOH. Now aromatic ring, just if I'm taking it as C6H5, then you get benzoic acid. From perbenzoic acid, you get benzoic acid, whereas one oxygen is used for addition to the double bond, CC double bond, to form the epoxide. Next, talking about the epoxidation with peracids, it is stereospecific in nature and it takes place by the syn addition to the double bond. So here you have to remember the addition is syn addition. So let us look into some examples. So here we have, let us take pH, here H, here I'm going to take methyl group, here I'm going to take H. So this is nothing but trans isomer, right? So in the presence of metachloroperbenzoic acid. So MCPBA, metachloroperbenzoic acid, right? So the epoxidation takes place. So here, what happens is H, here the pH, here H and CH3. Let us talk about cis compound. So here this is isomer if I'm going to take here CH3, H, H, and here I'm going to take the pH. This is the cis isomer. Again, in the presence of metachloroperbenzoic acid, the epoxidation takes place. So here you're going to get CH3, H, pH, and H, right? So in the case of, now in this case, it is very clear that syn addition takes place across the double bond, and you can see how the products are formed, how the epoxidation takes place, and how the products are formed. And you should remember that this particular reaction is stereospecific in nature. Next, talking about cyclic alkenes. So in this cases of cyclic alkenes, the reagent, it approaches from the less hindered side of the double bond. So this thing you have to keep it in mind when you're talking about where in the compounds the double bond is a part of a ring. So let us take the simple example. So here we have a cyclic alkene, right? So in the presence of metachloroperbenzoic acid, and we take a solvent, dichloromethane. So now what happens is the addition of oxygen, that is the epoxidation, it takes place from the less hindered side, right? The less hindered side of the double bond. So you get the products. So we have here, so epoxidation has to take place here. There is oxygen that is present, and here you have hydrogens, right? The hydrogens which are in this position. Next, you also get one more product, right? So here, again, epoxidation takes place, but here the hydrogens are in this way. Okay, so here you can see that there is the attack through the less hindered position. So we have this as the major product, that is 95%. Here, this is the minor product where it is only 5% that is produced, right? So next, coming on to dimethyl dioxyrane. Okay, this is another reagent which is used as an epoxidizing reagent. So let us take an example of a reaction. So CH2. So here we have this type of compounds. So this is called as an alene. So we have, okay, so dimethyl. So dimethyl groups, two methyl groups are there. Dioxyrane. So this is the oxyrane, dioxyrane. Okay, so we have on this reaction, we are going to get again epoxidation that is happening. So CH2, C. Here there are two double bonds, right? So since there are two oxygen atoms here in the reagent, so the two epoxide groups are formed because there are two double bonds also in the substrate. So we have again here CH2, So one more epoxide that is formed. So this is called as spirodioxide. Spirodioxide. Right. So this is about epoxidation reaction when we are talking about the alkenes. Next, talking about hydroxylation reaction. That is diol or glycol formation. So this also comes under oxidation. So we are first talking about oxidation reactions. Under oxidation of alkenes, we first spoke about how the epoxidation reaction takes place and what are the important reagents. Now talking about hydroxylation, that is formation of diols or glycols. So again, there are many reagents that can be used for adding two OH groups to the C double bond C. So some of the reagents are alkaline KMnO4, osmium tetroxide, as well as iodine, that is iodine and silver acetate that is used together. So these are the important reagents that are used to add two OH groups across the C double bond C. Now talking about alkaline KMnO4 as well as osmium tetroxide. So they give syn addition from the less hindered side of the double bond, and the reaction is again stereospecific, and here you're going to get, now suppose you're taking one, let us take one example. Okay, so here you have to remember these reagents. So when we are taking KMnO4, alkaline KMnO4 and osmium tetroxide, syn addition takes place, right? And again, you have to remember this occurs from the less hindered side of the double bond. And again, since the syn addition is taking place, one more thing you have to remember, this reaction is stereospecific in nature. Now let us take the example of cis-butene. You get meso-2,3-butane diol, whereas trans-butene, it gives DL, that is racemic mixture of 2,3-butane diol. Let's look into the examples for this particular syn addition. So we have C double bond C. So if I'm going to take the cis isomer, so in the presence of KMnO4 and again in the alkaline condition, so that's why I'm taking NaOH. So here you're going to get the product that is C double bond C. So here you're going to get C single bond C, the double bond will be broken. So here you have H, OH, OH, H, and here you have the R and R. So here again, you can see that the OH is adding to the double bond from the less hindered side. Here you can see there are R groups, right? Here there are only H groups. So what happens? The OH addition takes place from this side of the double bond. Next, talking about the trans isomer. So let us take one example. So here, this is a trans isomer. So in the presence of osmium tetroxide, and you can use hydrogen peroxide, again the syn addition takes place. So you can get here this, right? So here the double bond becomes single bond, and here you can see OH is added here. One OH is front, the bond is directed frontwards towards you, as well as the other bond is backwards, right? So you can see it very clearly. So here you get the DL, that is racemic mixture. Next, talking about the oxidation of norbornene. So here, oxidation of norbornene with KMnO4 in the basic medium, it gives 1,2-glycol, while in the neutral medium, you get a dialdehyde, right? So let us look into how this reaction takes place. So we have the norbornene. We have already taken this particular compound in one of the examples when I was explaining about the epoxidation reaction of alkenes. So when we talk about KMnO4, that is in the alkaline medium, we know that oxidation with KMnO4 in the basic medium, 1,2-glycol is obtained. So the double bond will be converted into the single bond. So you have H, OH, here you have H and OH, right? So next, if you're talking about KMnO4 in the neutral medium, so you're going to get a dialdehyde. So here CHO and CHO, right? So here what happens is the carbons that are involved in the double bond, so that bond itself breaks and you get CHO groups. Next, coming on to oxidative cleavage of alkenes by ozone, or in other words, we also call it as ozonolysis. Let us talk about how the ozonides are formed and how the cleavage takes place to give the carbonyl compounds. So we have RCH, C. Here I'm going to take the different R groups. Let us take it as R dash and R double dash. So you're going to treat it with ozone. So R, CH. Now the double bond, where the double bond is there, the ozone adds there. So we have O. Here the C, there is R dash, R double dash. Now here, this is called as the ozonide. So ozonide formation takes place by the addition of the ozone to the double bond, right? So now H2O2. So here, since you're using hydrogen peroxide, you're going to get RCOOH from this part, and you're going to get the ketone RCOR. So here R dash RCO double dash, right? So next, if you're talking about, let us take one more example, RCH. C. Again, I'm going to take the same substrate, ozone, in the presence of ethanol. So again, the ozonide formation takes place. Here we have R dash, R double dash. And here again, the ozonide formation. This is also this is the ozonide that is formed. Now, if I use zinc and acetic acid or dimethyl sulfide, so you're going to get RCHO from this part, and then you're going to get the ketone, R dash CO, R double dash. So you can see here very clearly, since here hydrogen peroxide is used, the aldehyde is not formed. Instead of aldehyde, the carboxylic acid is produced. Whereas here you're not going to use the hydrogen peroxide. Here you're just using zinc in the presence of acetic acid. So here you're going to get the aldehyde as well as the ketone. You're going to get the carbonyl compounds as the product. So here what happens exactly, here the bond shifts here, this shifts here, and here you can see this will be removed off. This is how you're going to get the carbonyl compounds as the products due to ozonolysis. So first the ozonide formation takes place and then the lysis takes place. Lysis is breaking of the bonds so that you get the respective products, right? So you can oxidize the ozonide by making use of silver oxide, hydrogen peroxide or peracids. So because of which you get the acid as well as the ketone. So in this case, the oxidation has taken place. So along with the hydrogen peroxide which you have used, instead of that, you can also use silver oxide or you can also use peracids for this particular purpose. Next, talking about before that, let me also add one more point. So ozonide can be reduced. So in this case, the reduction has taken place, right? Because one oxygen is lost. Here, there is no loss of oxygen. You get the RCOOH, that is the product that is formed. Here, the one oxygen is lost. So here reduction is taking place. So you can use zinc acid, right? You can take zinc along with any acid. That is one of the reagent. You can use triphenyl phosphine or you can use dimethyl sulfide, etc. So that you get the aldehydes and the ketones or the aldehydes based on what are the R groups that you have taken here, right? So suppose you use sodium borohydride or lithium aluminum hydride for reduction purpose, then you get alcohol. So you're not going to get the aldehydes as the product. Okay. So that is one thing you need to remember very clearly, because when we are talking about oxidation of the ozonide, so you can see here. So on oxidation, the ozonides will be converted into carboxylic acids or the ketones. Reductive workup, that is, if you are subjecting the ozonides to reduction, then what you're going to get, you can use these reagents as I've already told. So in the previous example, I've shown how zinc and acetic acid is used. So you can use PPH3, triphenyl phosphine, or dimethyl sulfide. So you can use where ozonides are converted into aldehydes and or ketones. So based on the R groups that you have taken, you get the respective carbonyl compounds. So instead of these reducing agents, if you're using lithium aluminum hydride and sodium borohydride, then you're going to convert the ozonides into alcohols. So please remember these three variants with respect to the ozonides, how it can be converted into the final products. Right. So now let us take one more example here. In the exocyclic double bond, so here let me take two methyl groups. Here there is a CH3 group, OH. Let me take one more CH3 group. So suppose you are subjecting this to ozonolysis. Again, ozone, you are treating it in the presence of ethanol solvent. And then the second step is you're going to reduce it in the presence of dimethyl sulfide. So you can see that whenever the ozone is added, we know that first of all, the ozonide formation takes place. Then here you have used the reducing agent. So reduction has to take place. If the reduction is taking place, then you're going to get the carbonyl compounds. So ozonide formation, how does it take place? So here CH3, here you're going to, this is remaining as such, CH3 as such. Here, what happens is, this remains as such. Here the ozonide formation takes place, right? So now we know that here, since you have used a reducing agent, the second step is the addition of reducing agent, right? So you have used this. So because of that, what happens now? The shifting of the bonds takes place here and this oxygen is removed off. So you're going to get the two products, that is both the products are carbonyl compounds. So here what happens is you're going to get double bond O, OH, CH3 and CH3. Along with that, you're going to get CH3CO, CH3, that is acetone. So easily you can predict what is the product just by looking at the reactant. Whenever we are talking about ozonolysis, just think about breaking the bond here. Now this particular part becomes one carbonyl compound. This particular part becomes another carbonyl compound. So just keeping this in mind, you can easily write what are the products. So here if I'm breaking this bond, see here, now we have got the double bond O. And here, since it was like this, since I've broken the bond here, this CH3 and CH3 remains as such, double bond O. So you got one more product, that is acetone. So based on this, you can easily predict what are the products that are formed. I hope it is clear. Yes. Let us move forward. Let us talk about oxidation of activated saturated CH groups. So till now we have studied about oxidation of the alkenes by epoxidation as well as ozonolysis in detail. Now let us talk about the oxidation of activated saturated CH groups. So saturated CH groups which are adjacent to the carbon-carbon multiple bonds or the carbon heteroatom multiple bonds. So these are the example of activated CH groups. So they should be adjacent to these groups, that is C double bond C, C triple bond C, or carbon heteroatom multiple bonds like C double bond O. So these different groups. So whenever the CH groups are adjacent to these particular groups, then we call such CH groups as activated CH groups. Right. So we have different examples like allylic groups, benzylic, as well as CH2CO, that is alpha carbonyl systems, which are under this activated CH groups. Now, first, let us talk about oxidation of the benzylic systems. So, let us take the example. So, we have CH3. Here, let me take one more CH3. So, you have to take for oxidation of this particular group. Now, look at this particular structure. See, this CH3 is nothing but CH3 like this, right? And which is connected to the benzene ring. I'm just writing it clearly. So here also CH3, right? Now you can see this CH as well as this CH bond. It is adjacent to the benzene ring, right? So here there are benzene ring, there are double bonds, alternative single and double bonds. Again, there is resonance, all that is secondary, but we know that here the CH bonds, even these CH bonds, right? They are adjacent to the, directly to the benzene ring. So because of which these CH bonds are activated CH groups. Correct? I hope you understood what is meant by activated CH group. Now, we take this particular compound, benzylic system we are taking into consideration. Now for oxidation of this, we are going to take acidified potassium dichromate. Or along with that, now whenever you're taking this potassium dichromate, or you can also take one more, that is KMnO4 in the acidic medium, and then you have to heat it. So you can use any of these reagents. Now, these activated CH groups will be oxidized directly to COOH, right? So if I'm going to take the other reagents, let us again take one more example. The activated CH groups, which are adjacent to the benzene ring, that is, we are talking about the benzylic systems. So you can use CrO3 in the presence of acetic anhydride and in the acidic medium, then followed on acidic hydrolysis. So in this case, if you're using a milder oxidizing agent, you're going to get the dialdehyde derivative. Okay, so when you're using strong oxidizing agents like potassium dichromate, acidified potassium dichromate, or acidified potassium permanganate, then the CH3 groups are directly oxidized to the carboxyl groups. Whereas if you're going to use milder oxidizing agents like CrO3, as well as in the presence of acid and on hydrolysis, you're going to get the respective dialdehyde derivative. Now, next talking about the allylic positions, how the oxidation takes place. So here, oxidation occurs at the allylic carbon. Again, we know that here the CH is activated CH group when it is in the allylic, which is near to the C double bond C group. So preferential oxidation takes place at the more substituted end of the double bond. So let us take one example. CH2, CH2. CH, double bond CH. Here I'm going to take the butyl. So here I'm going to take SeO2 as the oxidizing agent in the presence of pyridine and dichloromethane. So here what is going to happen is, now we know that the CH groups which are adjacent to the double bond. So here this particular CH group is adjacent to the double bond, right? So we have, now you see here 1, 2, 3, 4, 5. There are 5 carbon atoms this side, and here also there are 5 carbon atoms. So here, let us talk about again, when we are talking about the oxidation, so preferential oxidation takes place, but here there are, on either side, there are equal number of carbon atoms that are there. So one of these, since I'm taking only one mole, so here, one of the CH bonds will be converted to COH. So here you're going to get CH3, CH2, CH2. So this here, one of the CH bond is converted to COH, H, and then we have the remaining things as usual, right? So this is what happens. This is how the allylic oxidation takes place since it has a CH activated CH group. Next, talking about the oxidation at the CH2CO systems, right? So now, when I'm talking about how the oxidation takes place here, so first of all, we have to look into the common reagent that is used, that is SeO2. Okay, so activated CH group adjacent to the carbonyl group can be oxidized in very different types of ways that we can use. So first thing is, if you're talking about SeO2, how it can be used. So let me take an example, C6H5, CO, CH3. So in the presence of SeO2 and again dioxane and water. So now what is going to happen? Now look at these CH groups which are adjacent to the C double bond O group. So again, these are nothing but the activated CH groups. So here the oxidation takes place in the presence of SeO2. So you're going to get C6H5, C double bond O, CHO. So the oxidation of this particular group, which contains the activated CH groups, takes place in the presence of SeO2. So here, the reactivity of the methylene group is more than the methyl groups in case of the SeO2, whenever you're adding SeO2. So suppose if there was one more CH2 group that is present, then the reactivity will be much higher. Next, talking about oxidation of the unactivated CH groups. So if you're talking about the tertiary CH bonds, so oxidation of the tertiary CH bond to the COH bond can be achieved by making use of alkaline KMnO4. So let us take the simple example where the tertiary CH bond is present in the molecule. So let me take C2H5 here. Let us take CH3 group here. Here let me take C3H7 group and here the H. So it is very clear that this CH bond is the tertiary CH bond, right? Because this carbon is tertiary carbon, which is connected to three different carbon atoms. So it is a tertiary carbon atom, which is having a hydrogen. So this CH bond is tertiary CH bond. Now this selective oxidation of the CH to COH can be achieved by using alkaline KMnO4. So let us take KMnO4, alkaline conditions. So only this CH is converted to COH. Then all other groups remain the same. So CH3, C3H7, right? So this is with respect to the oxidation of the unactivated CH bonds. So under that, we are talking about how the tertiary CH bonds can be activated. Next, we have one more important name reaction, that is Hofmann-Loeffler-Freytag reaction. So in this case, the N-haloamines, so which have the hydrogen on the delta carbon. One more thing you have to remember. So N-haloamides, they should have a delta hydrogen, or in other words, they should have the hydrogen atom in the delta carbon. So only such type of N-haloamides, they give this particular reaction. Now here, the oxidation takes place at the unactivated delta carbon, which has the hydrogen. Now in this case, what is going to happen? Intramolecular cyclization will take place, and here you're going to get the product as nitrogen containing heterocycles. So we are taking the reagent, that is the reactant that we are going to take is N-haloamides. Now these N-haloamides on treating and one more important condition is that it should have the delta hydrogen that is present in the molecule. Now the intramolecular cyclization takes place, and here because of which you're going to get the nitrogen containing heterocycles as the product. So let us look into how this reaction occurs. So first let me take the compound N-haloamine, which has the delta hydrogen. So RCH2, CH2, I have to take one more and one more CH2. Then N-halo, so I'm going to take chloro group. And again, I'm going to take one more R. Let me take it as R dash. Now see here, this is alpha, beta, gamma, delta, right? So here you can easily see that there is a delta carbon which has two delta hydrogen atoms which are attached to this particular carbon. So, and one more thing is this is N-haloamine, right? And N-haloamine which has a delta carbon with the CH bonds that are present. Two CH bonds are present in the delta position. Now, this on reaction with H plus, that is acidification. So what you're going to get? So now what happens is this chloro group will attack this particular carbon. Okay, so this chloro group will attach to this particular carbon. So what you're going to get is CH, here Cl, and then the remaining things remain as such, CH2, CH2, CH2. Now here, since this has lost one chloro group, so this becomes plus charge. Now this will be neutralized with the H that is present in the acid. Now you get R dash, right? So now what happens is that next, the cyclization takes place by the removal of this H and Cl. So here HCl will be removed off. Now you can see that in the ring 1, 2, 3, 4 and 5. So you get a 5-membered ring along with which the nitrogen is also a part of the ring. So now nitrogen is attached to R dash. Keep it as such. Now we have this CH2, another CH2 group, this CH2 group, and one more CH group which is attached here because this CH group is attached to nitrogen, right? Because of the loss of Cl and H. So I'm directly connecting this. Now this CH is attached to R. So I have R that is attached here. So because of which now you can see a heterocyclic compound is formed which contains nitrogen in it. So this particular reaction is an important method of preparation of nitrogen containing heterocyclic compounds from N-haloamides. So I hope it is clear. Next, talking about oxidation of alcohols. So talking about the oxidation of alcohols, it is most useful and it is a widespread area of oxidation as it involves the oxidation reaction of alcohol to carbonyl compounds and then to the carboxylic acids in this particular sequence, right? So whether the resulting carbonyl compound, whether it is an aldehyde or whether it is a ketone or a carboxylic acid, it depends on the type of alcohol that is used as well as the oxidizing agent that we are going to use. So first let us talk about the oxidation by chromic acid and sodium or potassium dichromate. So what we are going to use as oxidizing agents. So here primary alcohols on oxidation with sodium or potassium dichromate in sulfuric acid, that is in the acidified medium, it gives aldehyde which are again further oxidized to carboxylic acids. Whereas secondary alcohols, they give ketones and these ketones are generally, they are resistant to further oxidation. They do not undergo oxidation so easily to give the carboxylic acids. So now let us look into this, some reactions with respect to this. So if I take a primary alcohol, so potassium dichromate, so I'm directly taking the dichromate ion in the presence of acid. So acidified potassium dichromate, right? So sulfuric acid I'm taking. So first you get RCHO, that is aldehyde from the primary alcohol along with that water. Then the dichromate ion is reduced to Cr3 plus because we know that dichromate ion is an oxidizing agent. So when it is acting as an oxidizing agent, it itself undergoes reduction, right? So dichromate ion gets converted to Cr3 plus, and of course we also have sulfate ion from the sulfuric acid. So let us balance the equation. So here we have 3 and 3. Then we have 4 here. So I'm going to add 4 also here. So here 2 are there. So I'm going to add 2 here. Now hydrogens, you can see 4 into 2. So it is 8. So here I have to add, yeah, along with that, the plus charges also have to be balanced. So I have 2 here and yes, 7 H2O, right? So now if I'm going to take further this RCHO, that is the aldehyde, again, since because here I'm using the dichromate, potassium dichromate in the acidic medium, so this aldehyde will be further oxidized to acid, right? So you have RCOOH, again, dichromate is reduced to Cr3 plus, and there are sulfate ions also, along with that water. So we have to see that the charges are also balanced on both the sides. So first I'll add 2 here. Next, this will be 3 and 3. So here I'm going to take 4. So here we have, since I've taken 4 here, this also will be 4. Now sulfate also will be 4 because 4 sulfuric acid I have taken. Yes, now it is balanced. Yes, so this is about how the primary alcohol will be converted to the aldehydes and then it will be converted to the carboxylic acids. Next, if I'm talking about secondary alcohols, as I already told, the secondary alcohol, they are first converted to ketones and ketones, they are resistant to further oxidation. So let me take a secondary alcohol. So here we know that the OH group is attached to the secondary carbon atom. So that's why we call it a secondary alcohol. Now this in the presence of sodium dichromate. So sulfuric acid, again water. So here you're going to get the ketone. So only this here the oxidation takes place. So here you're going to get CH3, C double bond O. Then the other groups remain the same. CH2 5 times CH3, right? Now this particular ketone is resistant to further oxidation. So because of which from the secondary alcohol in the presence of sodium or potassium dichromate in the acidic medium, you are going to get the ketones. Next, another type of reagent that can be used for oxidation is Jones reagent, which consists of CrO3 and sulfuric acid in acetone. So solvent that is used is acetone. So this is useful for the oxidation of the alcohols, which contains here especially the CC double bond or the CC triple bond or allylic or the benzylic CH bonds and other sensitive groups that are there. So when you're using Jones reagent, these sensitive groups will not be oxidized. Only it can lead to the selective oxidation of the alcohols to the, so if you are using primary alcohols, it will be oxidized to carboxylic acids. If you're using secondary alcohols, these alcohols will be converted to ketones, right? And this particular reaction has to be carried out at lower temperatures of 0 to 20 degrees Celsius. So let us take one example. So CH, triple bond, CH. Let us take one more double bond, CH, CH2OH. So in the presence of oxygen, that is because of the Jones reagent, so we have all these sensitive groups will remain as such, only the alcohol group will be oxidized. So CH triple bond C, CH double bond CH. So now here we have this CH to OH will be converted to COOH. Because it is a primary alcohol will be oxidized to acids. Next, let us take one more example, C4H9, C triple bond C. Here we have CH, OH. This is a secondary alcohol. So we know that secondary alcohols in the presence of Jones reagent, you're going to get the ketone. Sorry. Yes, C4H9, C triple bond C. Here now CHOH will be converted to C double bond O, and then you have CH3. So you have to remember that whenever Jones reagent is used, suppose the compound has some other sensitive groups like double bond C, C triple bond C, or allylic or benzylic groups, then only the alcohols, only the alcoholic groups will be oxidized, whereas the other groups will not be oxidized, right? So next, coming on to Collins reagent. So Collins reagent composition is again CrO3 along with that pyridine. So it is a complex, okay, complex of CrO3 and pyridine. So we call it as chromium trioxide pyridine complex. The other name for this is Collins reagent, and it is used for the oxidation of alcohols which contain acid sensitive groups, right? So in the previous case, we have used acid, right? Even in the Jones reagent, you are using the sulfuric acid along with chromium trioxide. Even in potassium dichromate or sodium dichromate, when you're using, you've used acids. So in case of compounds, in case of alcohols, which contain acid sensitive groups, then we can go for Collins reagent. So here, reaction is carried out in dry dichloromethane under anhydrous condition, that is in the absence of water. So let us take the example C6H5 CH CH CH2OH in the presence of CrO3 pyridine complex, that is Collins reagent. So we have C6H5 CH double bond CH. Now the CH2OH group will be converted to CHO, right? So here you're going to get this as cinnamaldehyde, right? Yes. Let us now look into the oxidation by using dimethyl sulfoxide. So we are talking about oxidation of alcohols. We are studying one by one. So we have studied about chromic acid and sodium or potassium dichromate. Under that, we have studied what happens when you use sodium dichromate, potassium dichromate in the acidic medium, along with Jones reagent and Collins reagent we have studied. Now let us talk about using DMSO, that is dimethyl sulfoxide, as the oxidizing agent. Mixture of triethylamine, DMSO, and oxalyl chloride. So this particular reaction or this particular oxidation is called as the Swan reaction. So when you're going to take this reagents, that is DMSO, oxalyl chloride, and triethylamine, we are going to facilitate the oxidation of primary alcohols into aldehydes. And this particular oxidation has this particular name, that is Swan reaction. Now this reaction, again, it is carried out in dry chloromethane at low temperature, that is below minus 30 degrees Celsius. So let us write the reaction. So C6H5, CH double bond CH. Here we have CH2, CH, CH3, CH2OH. Now I'm going to take the primary alcohol. So here we have DMSO, oxalyl chloride, COCl2 twice. Then we have triethylamine, and the solvent that is used is dichloromethane at low temperature. So we have C6H5, CH double bond CH, CH2. Here we have CH. This CH2OH will be converted to CHO. I'll just show it here itself. This is CH3. So here, selective oxidation of the primary alcohol to the aldehyde groups takes place in the presence of any other sensitive groups such as double bonds or triple bonds. So only this selective oxidation of the alcohols, that is primary alcohol to the aldehyde, takes place in the presence of DMSO. So alcohol, it can also be oxidized by DMSO by converting it into a tosylate ester. Alcohol can be oxidized by DMSO by converting it into a tosylate ester in situ. So now how it is done is, so first of all, the formation of tosylate, it is achieved in situ by the reaction of primary alcohol with tosyl chloride, that is represented as TSCl, in the presence of dicyclohexyl carbodiamide, okay, that is DCC, and it is followed by the addition of DMSO. So now, this is again specifically used for the oxidation of primary alcohols to the aldehydes. So let us take an example. So we take here bromo group. Here I'm going to take a primary alcohol group. So first step is you're going to treat it with tosyl chloride and DCC, that is dicyclohexyl carbodiamide. Then we have DMSO and sodium bicarbonate that is taken. So here, selective oxidation of CH2OH to the aldehyde takes place. So here you're going to get CHO group. So DMSO, it is also used to convert alkyl halides into aldehydes, right? So RCH2I. So if you're taking alkyl halides in the presence of sodium bicarbonate and DMSO, you're going to get aldehydes. So now, let us talk about oxidation of aldehydes. So till now, we have discussed about oxidation of alcohols in detail. So now let us talk about oxidation of aldehydes. So aldehydes, they are readily oxidized to carboxylic acid, and we can use the oxidizing agents, that is silver oxide, which is a selective oxidizing agent where it does not affect the other oxidizable functional groups. Let us look into certain reactions. We have C6H13CHO in the presence of, if I take KMnO4, H2SO4, that is acidified KMnO4, you're directly getting the acid, COOH, carboxylic acid. I can also write the general reaction, that is, if you're using acidified potassium dichromate, you're going to convert the aldehyde to carboxylic acid. Now talking about the silver oxide, which is a selective reagent, let us take some other functional groups that are present in the molecule. So let me take a double bond. Now if this aldehyde is subjected to oxidation in the presence of silver oxide, in the presence of a base, we have RCH double bond CH COOH. Suppose you take CH3CHO. You can also take other oxidizing agents. This is called as Tischenko reaction. That is, here what you're going to get is CH3, C double bond O, O, CH2, CH3. So here, two such acetaldehyde molecules are joined together. Again, this is also an oxidizing agent that is used. So Along with this oxidizing agent, the oxidation reaction takes place where two such molecules join together to form the ester. Right. So next, talking about oxidation of ketones. So let us take the general reactions. So R, C double bond O, CH2, R dash. So if I take alkaline potassium permanganate, I'm going to get R, COOH and R dash COOH. So this will be converted to one acidic group. This will be converted to one more carboxylic acid group. Next, if I'm going to take cyclohexanone in the presence of HNO3, which is again a strong oxidizing agent. So here the opening of the ring takes place. So we're going to get COOH, here CH2 4 times, then COOH. So totally there are 6 carbon atoms. So 2 COOH groups are formed, and in between the 4 CH2 groups will be present. So because of which you're going to get the open chain structure because of the HNO3 that is used, which is a very strong oxidizing agent. Now, if the ketones contain an alpha methyl group, they give the haloform reaction in the presence of the halogen and again in the presence of a base or in the alkaline conditions. So let us take one particular compound, that is COCH3, right? This is a ketone. So here there is a cyclopropene ring also that is present. So the two substituents are cyclopropene ring as well as the methyl substituent. Now you can easily see here there is a methyl group that is present, which is adjacent to the C double bond O group. Only such compounds where there is a methyl group adjacent to the C double bond O group of the ketone, only they undergo haloform reaction. So this occurs in the presence of any halogen. So if you're using iodine, we call it as iodoform reaction, or whatever we get, that is the iodoform that is formed. And H plus, that is on hydrolysis in the presence of acid. So you get COOH as the product. So oxidation of ketones can also be done to convert the ketones into esters and cyclic ketones to lactones. Okay, so ketones can be converted to esters, cyclic ketones can be converted to lactones by the treatment with peracids. So this particular conversion, this particular reaction is called as Baeyer-Williger oxidation. So let us look into the examples. So we have CH3, here CH3, CH3, COCH3. So we have the ketone. Now in the presence of peracid, COOH, 3 times you have oxygen that is present here. Now this CH3. Now here what is going to happen is that this CH3, C double bond O remains as such. One more oxygen will be added here. Then we have CH3, CH3 and CH3. So you can see very easily here that this is nothing but C double bond O. 2 oxygens are there, and on either side there are R groups. So this is nothing but the ester. So from the ketone, we are going to get the ester. So this particular reaction is called as Baeyer-Williger oxidation, and this is carried out in the presence of peracids. So one of the oxygen of this peracid is used to insert this oxygen into the ketone to form the ester. So similarly, the cyclic ketones can be converted to lactones. So we have the cyclic ketones. So let me take cyclopentanone, again in the presence of metachloroperbenzoic acid. Again, it is nothing but a peracid. So you get a lactone. So one oxygen will be inserted into the ring. So now first it was 5-membered ring. Now since there is one more oxygen that is inserted into the ring, now the ring becomes 6-membered in structure. Okay, so this particular compound has the name delta valorolactone, or you can just remember that the cyclic ketone will be converted to lactones because of the Baeyer-Williger oxidation in the presence of peracids. So this is with respect to the oxidation of ketones. So you need to use very strong oxidizing agents in order to facilitate the oxidation of ketones. Next, coming on to oxidation of carboxylic acids. Now, carboxylic acids on oxidation, they'll give carbon dioxide. So this process is also called as oxidative decarboxylation because carbon dioxide is released or it is removed. So decarboxylation, oxidative. Because of oxidation of this carboxylic acids, the carbon dioxide is produced, and this carbon dioxide, since it is in the gaseous state, it is removed off, right? So we call it as oxidative decarboxylation reaction. Let us take the example. Let us talk about the cyclobutane with the carboxyl group that is attached. So, in the presence of lead acetate, lead tetraacetate, and CHCl3, the presence of light. So, this COOH group is completely removed as carbon dioxide. Now, you get cyclobutane as well as carbon dioxide, right? Now, if you're talking about 1,2-dicarboxylic acids, they give alkene. Okay, so what happens is because of the removal of the C double bond O, this particular group, the COOH groups on both the carbon atoms, that is 1,2-dicarboxylic acid. So both the carbons are attached to the COOH groups. Now, because of the removal of this COOH groups on treatment with lead acetate, so CO2 groups are removed, carbon dioxide is removed. So because of which you get the alkenes as the product. So let us take the example. Here we have R. Let me take general example. Here also R and R. So here COOH and COOH, 1,2-dicarboxylic acids. So this on treating with lead tetraacetate and pyridine. So now what is going to happen? This as well as this is removed. So now we are going to get C double bond C, and then you're going to get the R groups which are present already attached to the carbons. So you're going to get the alkenes. So here it is alkenes, okay, not alkanes. 1,2-dicarboxylic acids when they are treated with lead tetraacetate, right? So next, coming on to oxidation of amines. So the most common reagents for the oxidation of aliphatic primary amines are H2O2, that is hydrogen peroxide, as well as you can use peracids. So let us take the examples. So CH3, CH2, CH2NH2. Let us take the primary amine. This on treating with hydrogen peroxide. So you get CH3, CH2, CH. Here you're going to get double bond N, OH. So we know that whenever there is C double bond N and the N is connected to OH, we call it as oxide, right? Now, this particular oxide, even when you're treating aldehyde with, so you're going to get the aldehydes with hydroxylamine, you're going to get the oxide with similar structure, right? So this is also an aldoxide. Next, let us take one more example, CH3, CH2 thrice, CH2, NH2. In the presence of peracid, so let us take CH3, COOH, right? So now we are going to get CH3, CH2 thrice, CH2. Now this NH2 will be converted to NO2, that is nitro compound. Let us take secondary amine in the presence of, again, hydrogen peroxide. So here what is going to happen is, this remains as such. Now this H will be converted to OH. Now we are going to get hydroxyl amine. Next, if I take tertiary amine in the presence of, again, hydrogen peroxide, methanol, or you can also use peracid. Here, the three R groups remain as such, unchanged, connected to the nitrogen. Now there is one more oxygen that is attached. Now this N becomes plus charge. Oxygen is having the minus charge. So this is how the oxidation of the amines take place by making use of various reagents. Especially we can use hydrogen peroxide and peracids for the oxidation purpose. Now the usual reagent for the oxidation of primary amines into aldehydes. Okay, primary amines, which can convert, the primary amines can be converted to aldehydes or ketones, okay, based on the groups that are attached. So based on that, the reagent that can be used is N-bromosuccinimide. So because of which, during the reaction, there will be imine derivatives, and from that, you're going to get the carbonate compounds. So let us look into the mechanism. So you take the primary amine. Now, N-bromosuccinimide, you're going to take it, NBS. I'm just writing it in short form. So now what is going to happen is, so here, this can be anything R. Okay, let me take it as R. So here, NH2. Now, this will be converted into the free radical, right? So this homolytic cleavage takes place, you get a free radical. Now here there will be a bromo free radical. So because of which you get now these two electrons will pair up. So because of which this becomes plus, because the electron is lost from carbon, the free radical, whatever one electron was there, that is lost. Now this NH2 remains as such. Now because here the free radical is lost, one electron is lost from carbon, right? Now this electrons, this lone pair of electrons can shift here to neutralize the charge on carbon. Along with that, you have Br minus, because this electron and one electron of bromo free radical, they both combine to form Br minus. Now it becomes C. Here, let me write it as R and R, R, R. So here we have double bond. Now, since it has, the lone pair of electrons has been shifted here, I get NH2. This will be plus charge, correct? So now, one H plus can be removed because here there is a plus charge. Now, one H plus can be removed to neutralize this particular charge. So, minus H plus. So, I have C, here R and R. Here double bond, N. And one H plus has been removed. So, now there is only one H. Now, if I add water, the hydrolysis will take place. So you have C double bond O, R and R. Okay. So again, now here, based on here, I have taken both as R groups. Now, if one of the R groups, instead of R, if I have taken as H, then you get aldehyde as a product. Now, if both are R groups which are attached to this carbon atom, then you're going to get the ketone as the product. So this is with respect to, by making use of N-bromosuccinimide, how you are going to get the aldehydes or ketones from the amines taken in the as a starting material. Okay. Now, aliphatic primary amines can also be oxidized by making use of 4,5-ditertiary butyl orthobenzoquinone. So here what happens is, this particular reagent, it selectively oxidizes aliphatic primary amines, and it is effective only when the alpha carbon of the amine is secondary. That is, where the alpha carbon is attached to two carbon groups. Let us look into this particular reaction. So here, NH2, here, this is the alpha carbon. Now, this particular reagent, that is 4,5-ditertiary butyl orthobenzoquinone, it only acts on the amines, the primary amines, where the alpha carbon, this is the alpha carbon, right? It should be attached to two carbon atoms, or it should be secondary, right? So now, in the presence of this particular reagent, so let me write the structure. So you have double bond here, double bond here. Here we have the double bond. So tertiary butyl group. Here also tertiary butyl group, right? So we have 4,5-ditertiary butyl orthobenzoquinone. So here it is ortho position, right? So orthobenzoquinone, right? Okay. So now this is the reagent that is used. So this is, let me write it as 1. So again, the second step is the same, hydrolysis, acid hydrolysis. Now, here what happens is, you're going to get the ketones as the product, right? So selectively, the oxidation of aliphatic primary amines takes place. Now here, One more condition is the alpha carbon should have two alkyl groups that are attached, alkyl, or in general, two carbon atoms should be attached to this alpha carbon. So here you're going to get the ketone as the product. Okay, so this is with respect to the oxidation of amines. So here we come to the end of oxidation. Now next we are going to start with reduction. So about oxidation, we have studied in detail about oxidation of hydrocarbons. That is, specifically we spoke about oxidation of C double bond, the alkenes by epoxidation, as well as by making use of how the poracids can be used, and also about ozonolysis. Then we also discussed about the CH activated group and unactivated CH groups, how it can be, how these groups can be oxidized. Then we discussed about oxidation of alcohols, oxidation of aldehydes, ketones, carboxylic acids, and also about the amines. Now let us start understanding about the reduction reactions. Now reduction, we know that it is addition of hydrogen or removal of oxygen or the gain of electrons by by an organic compound. When we are talking about here specifically, we are talking about the reduction of the organic compound. So these are the different ways of defining reduction. So general reaction, if I have to write, RCH double bond CH2. If I add hydrogen, what is going to happen? Again, in the presence of a catalyst. So this is catalytic hydrogenation reaction. So here you're going to get RCH2CH3. Here the addition of hydrogen has taken place across the double bond to give the product. Here alkene is converted to alkane because of the addition of hydrogens. Now first, as we have studied for oxidation, let us start with understanding the reduction of hydrocarbons. First, again, like that of oxidation, let us start with understanding the reduction of alkenes. So by catalytic hydrogenation reaction. So this is the most convenient methods for the reduction of alkenes, where the alkene in the presence of hydrogen and in the presence of a suitable catalyst, they result in the formation of alkanes, right? And now hydrogen adds by syn addition, and again this particular reaction is also stereospecific. So we have the general reaction C double bond C. So this can be anything, it can be H or the R groups that are attached. So in the presence of hydrogen and in the presence of catalyst, H2 should be there because it is reduction, right? So in the presence of catalyst, so this is catalytic hydrogenation reaction. So we have the H will be added here. Double bond is converted to the single bond. Now again, the addition of hydrogen is syn addition. And again, the reaction is stereospecific in nature. So we have C double bond C. Let us take the examples. So pH, here we have CH3, CH3, hydrogen in the presence of palladium. You can also take platinum, nickel. All of these are the catalysts that are used for hydrogenation. So we have C double bond C here. H is added, both the hydrogen atoms that are added. So we have pH, here pH, and these two bonds, here CH3 and CH3. Next, if I'm talking about here the trans isomer, so CH3, pH. Let me take pH here and CH3 here. This is the trans isomer. Again, hydrogen in the presence of the catalyst, PD. Now, C here, bond. Again, H and H. Now, again here, the pH. Here there will be CH3. And these two bonds here, here we have CH3 and here we have pH. Right? Now, you can also take one more example. So suppose we have this particular compound. So here we have Cn and here we have CH double bond CH2, hydrogen and palladium. So here you're going to get CH2, CH3, the double bond is reduced and this remains as such. Right. Next, we have a specific important catalyst, that is Wilkinson's catalyst, that is rhodium complex, which has the triphenyl phosphine groups, 3 triphenyl phosphine groups and 1 fluoro group. It is the most useful homogeneous catalyst for the hydrogenation of alkenes. So let us look into it. So if I have C double bond C here, R, R, R dash, here let me take R dash. Again, hydrogen is added, so hydrogenation reaction. In the presence of Wilkinson catalyst, RCl, PPH3 thrice. So again here, the hydrogen is added. Then we have R, R dash, again R and R dash, right? So you can also take one more example, the cyclic compound. So here we have, yes. So now what is going to happen? This particular double bond is only reduced, which is easily susceptible for reduction. So H2 in the presence of again RH, Cl, PPH3 thrice. So in the benzene taken as a solvent. So here in this case, these double bonds, this particular double bond is not reduced, which is inside the ring. So this double bond, which is outside, it is easily susceptible to reduction. So you're going to get the reduced product, right? Next is reduction of alkynes. So here also we are talking about catalytic hydrogenation. So here alkynes, as we know, are, here I'll take R again. So triple bond is there. So hydrogen in the presence of catalyst. First, it is converted into alkene. Next, again, these alkenes in the presence of hydrogen and catalyst, because here there will be enough amount of hydrogen and catalyst that is present in the reaction mixture. So here we have RCH2, CH2, R. So finally, the alkynes will be converted to alkane on reduction in the presence of hydrogen and catalyst. That is on catalytic hydrogenation reaction. So this particular reduction can be stopped at the alkene stage by using palladium, okay, palladium, which is poisoned with barium sulfate. So this particular catalyst is called as Lindlar's catalyst. So in which using this particular catalyst, you can stop the reduction process at the alkene stage itself. Or you can also use nickel boride, that is P2, Brown's catalyst, which is also called as P2 catalyst or Brown's catalyst. So again, you can stop the reduction using any of these catalysts for reduction of alkyne at the alkene stage. So here it produces cis alkenes by syn addition, and the reaction is stereoselective again because the syn addition takes place and you're going to get the cis alkenes as the product. So let us take the example CH3, CH2. Here we have C, triple bond C, again CH2, CH3. In the presence of H2, that is again Lindlar's catalyst is used. So Lindlar's catalyst is nothing but palladium in the presence of barium sulfate, right? And you can use quinoline. So here, as I already told, cis alkenes are produced. So both the H atoms will be here, H groups. Then we have CH2, CH3 groups on the same side, right? So here, what is this? You can see 1, 2, 3, 4, 5, 6. There are 6 carbon atoms, and in the third position, there is double bond. So we have 3, 4, 5, 6 hex, right? So 6, 3 hexene. Or you can also call it as cis hex 3-ene. So here, this is a major product that is 95% yield. Right. So here the reduction of alkyne in the presence of Lindlar's catalyst, because of this, it is stereoselective in nature. Next, you can also use boranes for the reduction of alkynes. So this reaction is also stereoselective, and here the addition is also, here also it is the syn addition. So let us take an example. So C6H5, C, triple bond C, C6H5. So first step is we are going to take BH, DHF, then we take CH3, COOH, and heat, right? So we are going to use boranes for this particular reduction process. So here, again, you're going to get the cis isomer, H and H. So you're going to get cis alkene, right? So this particular SiA2BH, the name of this is nothing but dicyamyl borane. Dicyamyl borane. Okay, so it is a sterically hindered dialkyl borane. So because of which you get the syn addition occurs, and because of which you're going to get the cis alkene as the product. Again, reduction can also be carried out by making use of group 1A metals in the presence of liquid ammonia. So non-terminal alkynes, it reacts with a solution of group 1A metals such as lithium. It can be even sodium or potassium in the presence of liquid ammonia. So here you should remember we are going to get the trans alkene as the product. So this particular reagent is also used to stop the reduction process at the alkene level. So here again the further oxidation to alkane does not take place, but here you should clearly remember that the alkene that is produced is trans alkene. So let us write the reaction here itself. Let me write it here. So we have CH3, CH2, C triple bond C, CH2, CH3 in the presence of sodium and liquid ammonia. So here you're going to get the trans alkene. So here if I write CH2, CH3, here there will be CH2, CH3, H and H. So here you're going to get the trans alkene as the product. So whenever you're using group 1A metals in the presence of liquid ammonia. Okay, so to get cis alkene, we can use the palladium in the presence of barium sulfate, Lindlar's catalyst. For getting the trans alkene, we are going to use this group 1A metals in the presence of liquid ammonia. Right. So next, talking about reduction of aldehydes and ketones. So reduction with hydride transfer agents, reagents, this is very, very important. So most of the cases in organic chemistry, we will be coming across these reagents. So common reducing agents are sodium borohydride, lithium aluminium hydride. So lithium aluminium hydride, it is generally used in the dry ether solution. And sodium borohydride is comparatively a mild reducing agent which reduces only aldehydes and ketones. And it is comparatively more selective because it does not reduce C double bond C, C triple bond C, N double bond N, esters or nitriles, or whenever these functional groups are present, you can easily use this sodium borohydride because it does not reduce these functional groups. So it is only acting on the aldehydes or the ketones. Let us take the simple example with various functional groups that are present in the molecule. So here we have COO, C2H5, the ester group. Here we have the ketone group, CH2, C6H5. And here we have a ring also. Along with that, the nitrogen is a part of the ring. Now, if I use sodium borohydride, NaBH4, and again, the second step is always, in this case, the acid hydrolysis. Now, the ring remains intact. Only this double bond O, which is a ketone group, is reduced to OH group. Here, all the other groups remain the same. C6H5, here COO, C2H5, right? So this is with respect to the reduction of aldehydes or ketones with sodium borohydride. Now, aldehydes and ketones, they can also be reduced using borane, right? So borane BH3 can reduce aldehydes and ketones. So they will be reduced to alcohols. So let us look into how it takes place. So let me take a ketone. So I'm going to take R and R dash. So when you're using borane BH3, right? So here, the lone pair of electrons, whatever is present in oxygen, it first attacks the boron. So we know that boron here is electron deficient. So this lone pair of electron can easily attack the boron atom. So now this remains as such R and R dash. So here this double bond O. Now, since this has been used for attacking boron atom, this becomes plus charge. Now here, boron is attached. There is H, H, and H. Now this becomes minus charge. Now what happens is this bond, it attacks here, and this double bond shifts here. So now what is going to happen? Carbon, already the R and R dash groups are there. Now since this bond is attacking here, the hydrogen is attached to the carbon now. This double bond becomes single bond, and here it is BH2. Now on hydrolysis, that is in the presence, we know that the second step is hydrolysis, right? So H2O. Now what is going to happen? R, C, R dash. Now H is already there, which is attached to carbon. Now here you're going to get OH. So you're going to get the alcohol from the, here you're going to, this is the ketone. So from ketone, you're going to get the secondary alcohol. So let us take the example C6H5, CO, CH3, in the presence of diborane, B2H6, DHF as a solvent. And the second step is hydrolysis, as I already told you. So here you're going to get CHOH, C6H5, CH3. So this is with respect to the arrangement of the bonds. So here it will be OH, C6H5, CH3. This will be, I'll just write it clearly. Okay, like this. Yes. So this is with respect to the reduction of aldehydes and ketones by making use of boranes. Next is aluminium isopropoxide. So this also is a very good reagent that is highly specific for aldehydes and the ketones. The other groups, if they are present, they are susceptible to reduction if they are present in that particular compound. They are not reduced by this particular reagent. And this particular reaction or this particular reduction is called as Mirvin-Ponndorf-Verley reduction. Verley reduction. Right? So let us take an example. So we have CHO and NO2. So now if I use this particular aluminium isopropoxide reagent, that is Al, aluminium isopropoxide reagent in the presence of isopropanol. So we have only the CHO group is reduced. So we have CH2, OH, and NO2 remains as such. Although NO2 can be reduced further, it is not going to be affected in the presence of this aluminium isopropoxide reagent. And this particular reduction reaction has the special name Mirvin-Ponndorf-Verley reduction. Right. So next is reductive cleavage of the carbonyl group. So carbon-oxygen double bond, how the reductive cleavage can take place. So the CO group of the aldehydes or the ketones can be reduced to CH2 group. So mainly by two different types of reactions. One is Wolff-Kishner reduction and the other one is Clemmensen reduction. Here the main difference between these both is Wolff-Kishner reduction is carried out in the presence of the alkaline medium, whereas Clemmensen reduction is carried out in the acidic conditions. But the products remain the same. Here, the C double bond O group is converted to CH2 group. Right? So this is one thing you need to remember. The direct conversion of the carbonyl group to the alkane. So here the aldehydes or ketones will be converted to the CH2 group. C double bond O group is converted to CH2 group. And this method here, Wolff-Kishner or Clemmensen reduction can be done. The only difference is with respect to the conditions that are maintained in the reaction. So we have here, let us take the example CO, CH3. So Wolff-Kishner reduction. So I'm going to take NH2, NH2 in the presence of KOH. So glycol, heat. So we have here the C double bond O group will be converted to CH2 group and get CH3. This is Wolff-Kishner reduction. Next, cyclobutane ring, CHO group. Here we have C2H5. Here also let me take C2H5. Just to show that whenever there are other groups, susceptible groups that are present, how the selective reduction takes place. In the presence of this Wolff-Kishner, these reagents, that is by making use of Wolff-Kishner reduction or Clemmensen reduction. So again, I can take glycol and heat. So the other groups remain as such. Now CHO is converted to CH3 group. The other groups remain the same. OC2H5, OC2H5. Clemmensen reduction, I'll just show it here. This is also Wolff-Kishner reduction. Clemmensen reduction, RCO, CH3, just the general reaction I'm going to show. So zinc amalgam, concentrated HCl. As I already told, here acidic conditions are used. This is Clemmensen reduction. So you're going to get RCH2, CH3. This is Clemmensen reduction. Right. So this is with respect to the reductive cleavage of the carbonyl group. So how the C double bond O group can be converted into the CH2 groups. Next, coming on to reduction of carboxylic acids and their derivatives. So here, if I take the carboxylic acid and treat it with lithium aluminium hydride, so what is going to happen is, so this is the carboxylic acid. So lithium aluminium hydride, it's nothing but aluminium. So one hydride will be there. Hydride is H minus. So here let me write this C double bond O, O minus, here Li plus. So this H can be easily removed as H plus because it is an acid. H plus is easily removed. Carboxylate ion is formed. Now this, the O minus is stabilized by the Li plus, the ion of the lithium aluminium hydride. Now this is having minus charge because Li plus and AlH4 minus. Now this along with this can be attacking the carbonyl carbon and the bond shifts here. So you have R, C, here O, Al, H3 that is attached here. So you have H that is attaching here. Then we have O minus, Li plus, right? Now this O minus can come here. This we do not require. This can be removed off. So we have R, C, here this becomes double bond, right? So double bond and there is a H that is attached. So we have H that is aldehyde. Now again, if it is treated with lithium aluminium hydride and again followed by hydrolysis, acid hydrolysis, aldehyde can be further reduced to alcohols, primary alcohol. So here you're going to get alcohol. So carboxylic acids on treating with lithium aluminium hydride, first they are converted to aldehyde and then it is reduced to the alcohol. So if it is, so aldehyde on reduction, they give primary alcohol as the product, right? Now the order of reactivity of the acid and their derivatives in this particular, for this particular reaction is R, COCl will be maximum. Then we have R, COO, COR. Then we have RCOR, that is for esters. Then we have RCONH2, that is acid amides. And then it will be for carboxylic acids. So acid chlorides will be highly reactive. Then we have anhydrides. Then we have the esters, acid amides, and then the carboxylic acids. So we can write one reaction with respect to this. Yes, let me write it here itself. I'll just erase this and write. With respect to the reduction of the acid derivatives. Yes, so let us take one example. So here we have OH group, here COOH, and here we have methoxy group. So if it is treated with lithium aluminium hydride and followed by hydrolysis, so this acid group is reduced. So this OH remains as such. Methoxy group remains as such. COOH is reduced to alcohol. So CH2OH is reduced. So next, talking about the common reducing agents, we have diisobutyl aluminium hydride. That is what we have talked about. Dibal H. That is one more reducing agent that can be used along with lithium aluminium hydride. Now, diisobutyl aluminium hydride is a type of alane which can also reduce the acids and their derivatives. Right now, again, when you're using this allenes as the reducing agents, the order of reactivity will be different. Where the acids will be highly reactive, the carboxyl group, then it will be the acid amide, then will be the esters, and least will be for the acid chlorides. So that is also one thing you need to remember when we use the allenes as the reducing agents. Now this dibal, it is the most important alane. So you can use this dibal H as the reducing agent. So CH3, CH2, CH2COOH in the presence of dibal H, diisobutyl aluminium hydride. So in benzene solvent, 25 degrees Celsius. So you're going to get the alcohol, CH3, CH2, CH2, CH2OH, right? So this is with respect to the presence of dibal, the usage of dibal as the reducing agent. Now, lithium aluminium hydride, if you're talking in specific, it is a very powerful reducing agent for most of the organic functional groups, and it reduces carboxylic acids and their derivatives to alcohols. I've already explained the mechanism for this reaction, right? So let us look into the examples. So COO, C2H5. So you take lithium aluminium hydride. You take water, that is hydrolysis. So C6H5. Here the double bond also is reduced. So you're going to get CH2. Sorry. Now here it will be single bond CH2 double CH2 single bond CH2. Now this COO C2H5 will be reduced. So you're going to get here CH2OH. So then you're going to get C2H5OH, right? So you can also, next talking about reduction in the presence of reduction of nitriles. So how it is done? So reduction of nitriles, mainly the nitriles are converted into aldehydes. Okay, so how they are converted into aldehydes, this particular reaction is called as the Stephan reduction. So this particular reaction is also an important method of preparation of aldehydes from nitriles. So how it is done is, so first when you treat the nitriles with an acid, that is HCl, here you're going to get Cn, this becomes double bond NH. Now, you treat it with SnCl2, again HCl at 20 degrees Celsius. Now, you can see that here you get RCH double bond NH, right? Now, this on hydrolysis and again on heating, you're going to get RCHO. So, the nitrile is converted to aldehyde. So, this particular reduction is called as Stephan reduction. So, we can also take one more example. So, we take here, again Cn group is there, which will be reduced. So if you take dibal here and the acid hydrolysis, just you can imagine what is the product that is formed. Just we have discussed about dibal. So dibal can also reduce the Cn group. So you're going to get the aldehyde. So this NO2 remains as such. Dibal is more specific. So here only Cn group is reduced to aldehyde. And yes, this is the product that we get it. Okay. So this is with respect to the reduction of nitriles where the nitriles are reduced to the aldehydes. First is by Stephen reduction. You can also use dibar for the reduction of the nitriles to the respective aldehydes. Now, the reduction of nitriles can also be done into amines. How it is done is, so here, so before that, here only I'll just erase this particular equation and I'll show the reactions here itself. So if you take nitriles and treat it with hydrogen, so first what you're going to get, here you're going to get RCH double bond NH. Now again on treating with hydrogen, you're going to get RCH2 NH2. Similarly, RCH2CN. If you're treating it with hydrogen in the presence of catalyst, on catalytic hydrogenation reaction at high temperature and high pressure, again, you're going to get the amines. So here, again, there is one more carbon atom. So CH2, NH2. Next, RCN. Again, on addition of hydrogen, that is by using lithium aluminum hydride, ether, you're going to get RCH2, NH2 as the product. Right. Next, when you're talking about isocyanides, so these isocyanides can be reduced to secondary amines either by making use of sodium in the presence of ethanol or by catalytic hydrogenation reaction. So these are the reagents that are used. So you take isocyanide, that is RNC, in the presence of hydrogen. So you can use one of these reagents, that is sodium and ethanol. So you get RNHCH3. So you're going to get primary amine from this. This is nothing but isocyanide. Right. So this is with respect to the reduction reactions, which I've explained in detail with respect to the reduction of hydrocarbons, the reduction of carbonyl compounds, carboxyl groups, as well as its derivative, the carboxylic acids and its derivatives, and also about the nitriles as well as the isocyanates. So how the reduction occurs, what are the various reagents that have to be used, and what are the expected products. Right. Now on to common catalysts and reagents in organic synthesis. So let us start with lithium dimethyl cuprate. So the formula is lithium Li, copper Cu, CH3 twice. So dimethyl, so that's why CH3 twice. Now this is, as the name indicates, and according to the formula, we also know that it is an organometallic reagent. It is a source of carbanion and hence because of which it is widely used for alkylation, mainly by nucleophilic mechanism. Now it is prepared again starting from the alkyl halide and it is again a Gilman reagent. So the organocopper reagents are commonly called as Gilman reagents. Now let us see how to prepare this. So we take the alkyl halide in the presence of lithium. You are going to get CH3Li. Now CH3Li on treating with copper iodide, you're going to get CH3 twice CuLi plus lithium iodide. So I'm balancing the equation. Yes, this is how you prepare lithium dimethyl cuprate. Now talking about the applications of this particular reagent, it is used in the nucleophilic substitution, nucleophilic addition reaction, as well as conjugate 1,4 addition reactions. So let us look into the reactions in which this particular reagent is used. So we have RCO, CH2, CH2I, plus this particular reagent, that is lithium dimethyl cuprate. So here we can see that RCO, CH2, CH2, CH3. So you can see that one of the CH3 groups from this particular reagent is added to the substrate molecule. Right. Next, let us take another example. So we have here Cl. So CH3 twice CuLi. This is a reagent that we use. So now we have here whatever the Cl is there, that is replaced by the CH3 from the reagent. Next, let us take one more this substrate. So now here we have OAC, which is a good leaving group. So again, I'm going to take the reagent. So we have, so this will be removed off. So this double bond can shift here, and this is a leaving group, so it can be removed off easily. So you have here, these things remains the same. So this becomes a double bond, and here, sorry, here there will be CH3 group that is attached. If I take iodobenzene, right? Now there is iodo group here. So this can be replaced by the methyl group by making use of this reagent. So iodine is a halogen. It can be replaced by the CH3 group. Next, I can also take here OH and here epoxide. There is CH3 twice CuLi. So this results in opening of the epoxide. So you have H and you have CH3. Right. So this is how this particular reagent, how it can be used for the nucleophilic substitution, nucleophilic addition, as well as conjugate addition reaction. Now this particular reagent, it also reacts with alpha beta unsaturated carbonyl compounds, and they give 1,4 addition products. So let us see how this addition, 1,4 addition reaction takes place. So a carbonyl group. So here we have the R group. So if I take the reagent, that is lithium dimethyl cuprate, so CH3 twice CuLi, and on acid hydrolysis. So now 1,4 addition takes place. So this double bond remains as such. Here this double bond. So here the addition takes place. So here R is already there and the CH3 adds here. Next, let us take one more example. So here I take CH3. Here I take the methoxy group. Now if I add lithium, the presence of ammonia, tertiary butanol. So what is going to happen? We know that here OCH3 and here CH3. So this can be converted to, here this becomes double bond. This becomes CH3. This is CH3 as such. And here there will be conjugation. And on addition of CH3 twice CuLi, the CH3 group will be added. So here you can see there is a double bond which is in conjugation with the C double bond O. So already there is a CH3 group. One more CH3 group will be added to this particular carbon atom. So this is with respect to 1,4 addition. They also bring about nucleophilic substitution reaction with procylates. So let us take the example. So here, if you add this particular reagent, so here the substitution takes place and you get RCH3 as the product. Next reagent which we are going to study is N-dicyclohexyl carbodiamide, which we have already come across. This is also dehydrating agent and it is stored under anhydrous conditions. So it is prepared by the oxidation of dicyclohexyl urea using para-toluene sulfonyl chloride in hot pyridine. So we have here. So first of all, we know that this is N-dicyclohexyl. So we have dicyclohexyl, carbodiimide. So these are imide groups. So carbodiimide. Or you can also write it as C6H11 N C double bond N C6H11. Let's see how the oxidation is done. C6H11 NH CONH C6H11 So dicyclohexyl urea. So urea is NH2CO NH2. So when one H is replaced by cyclohexyl group, we get dicyclohexyl urea in the presence of para-toluene sulfonyl chloride. So we have CH3, C6H4, SO2Cl, that is para-toluene sulfonyl chloride. And in the presence of hot pyridine, you are going to get this particular reagent, that is DCC. C6H11N double bond C double bond N, again C6H11. So coming on to the applications of DCC. So it is a versatile reagent that can be used and it can bring about condensation reaction very smoothly. It can also practically bring the two reacting groups together. So smoothly the condensation reaction can take place in the presence of this DCC. So it also promotes these particular reactions because of this particular property. So etherification, esterification, amidation, lactam formation, and lactamization, all these reactions can be facilitated in the presence of DCC. So let us take a certain examples. So let us take phenol C2H5OH in the presence of DCC at 100 degrees Celsius. So pH, so we know that it is a dehydrating agent, powerful dehydrating agent. So we have PHO C2H5 and water molecule is removed because DCC mainly helps in the removal of water molecule. So alcohols can also be reduced to hydrocarbons in the presence of DCC. So if you have ROH in the presence of DCC, you get DRH. Similarly, RCOOH, CH2N2, in the presence of DCC, you get RCO, CHN2, which is nothing but diazoketones. Okay, so from carboxylic acids, you can obtain diazoketones with the help of this DCC. So yes, this deoxygenation of alcohols to hydrocarbons I've already explained. So where ROH is converted to RH. Next, talking about lithium diisopropylamide, that is LDA. So LDA, how it is prepared? So first of all, we know that the formula is LIN, isopropyl groups. There are two isopropyl groups. Now, how it is prepared? It is prepared from diisopropylamide and N-butyl lithium in the presence of THF at 0 degrees Celsius. So isopropyl group is, this is isopropyl group. So diisopropyl, so 2 times NH. So what we are going to do, we are going to take diisopropylamide. So this is diisopropylamide. I'm going to treat it with N-butyl lithium. So butyl lithium or N-butyl lithium in the presence of THF and 0 degrees Celsius. Now we are going to get this lithium diisopropylamide as the product. So the isopropyl group remain as such. 3 twice. This I'm going to keep it as such. Now N here, to this the lithium is attached. Then we have the butane. Right. So now coming on to the applications of this LDA. So it is a very strong base and it abstracts hydrogen from the active carbon. So let us take the example here. Right. So we have the example where there is active carbon. So this LDA, it can abstract the proton from this active carbon. So you get CH2, double bond C, double bond C. Here one of the hydrogen is abstracted. So you get minus here, here Li plus. So it is also used in the generation of carbanion. So for example, now R, CH2, COR dash. In the presence of LDA, you're going to get R, C, H. One of the hydrogen is abstracted, so you get minus charge here, COR dash. So this can be treated with R double dash X. Let us take some alkyl halide. So you're going to get R, CH, R double dash, here COR dash, right? So this is a very powerful base and it can abstract the proton from even mainly the active alpha hydrogen atoms can be abstracted by making use of this LDA. Next, talking about the sulfones as well as sulfenic esters, they can also be alkylated. Even the benzylic carbon atom alkylation can also take place. Again, we can also go for alkylation and acylation of the carboxylate ions. So these are the different applications of LDA. Let us look into the equations one by one. So let us look into how the alkylation and the benzylic carbon can take place. So we have COO minus, then we have this CH3 in the presence of LDA. Now what happens is the active hydrogen can be abstracted. So this already it is COO minus. Here there is hydrogen which can be abstracted. So you have CH2 minus. All this remains as such. Now if Rx is added, the alkyl halide, now what is going to happen? Here there is a minus charge, right? So R comes and attaches there. So COO minus. Here we have CH2R. Now talking about sulfones and sulfenic esters. So PH, S double bond O, CH, here R. Here we have CH double bond CH, R dash. In the presence of LDA, again if I take the alkyl halide, right? So what is going to happen here is, so PH, here S double bond O, so here C. Now this hydrogen can be abstracted by LDA. So already there is one R. Now this R double dash will go and attach there. So CH double bond CH R dash, right? Next, talking about alkylation and acylation reactions. So if you're taking carboxylate ions, COO minus, in the presence of LDA, now this hydrogen has to be abstracted. So RCH minus COO minus. If I take alkyl halide, now what is going to happen? This R dash will come and attach here. So R dash H COO minus. Similarly, acylation also can be carried out. So RCH2 COO minus. In the presence of LDA, we have RCH here minus COO minus. Now, if I have to acylate it, so I have to take R dash COO ME. So this part will come and attach there to this particular carbon. So we have R CO CH R COO minus. Right. So this is how the acylation as well as the alkylation takes place. Next, coming on to tri-N-butyl tin hydride. So this reagent is again, it is specific for the reduction of carbon halogen bond to the CH bond. So this thing you have to remember, CX to the CH bond conversion is carried out in the presence of tri-N-butyl tin hydride. So how it is prepared? So it is prepared by the reduction of tri-N-butyl tin chloride or tri-N-butyl dioxide with lithium aluminium hydride. So let us look into how it is done. So N-butyl, so C4H9. So tri-N-butyl is present, so 3 times. So tin chloride I'm going to take in the presence of lithium aluminium hydride. So ether solvent, refluxing is done. Then water is added. Then you're going to get this particular reagent. That is tri-N-butyl tin hydride. Right. So the chloride is replaced by the hydride. Next, coming on to the applications of this particular reagent. So this reagent can be used for alkyl halides, acyl halides, diazonium salts, aromatic halides. For all of these, so reduction can be done by making use of this particular reagent. So let us take the example. So here, in the presence of this particular reagent, that is tri-N-butyl tin hydride, right? So you have here, what happens is alkyl halides can be reduced. So here there is an alkyl halide group, right? So it will be reduced to CH3. Now this is CH2, O, CO, CH3. Along with that, you also get N-butyrice SnCl. The chloro group is removed. In that position, you have the H that is added. If I take one more example, So here, chloro group, if there is H here, in the presence of this particular reagent, SNH. So here, you're going to get the Cl is replaced by H. Okay, so here you have H and here you have H. So along with that, you have NBu thrice SnCl. Along with that, even the unsaturated acids can be converted into saturated lactones, right? So how it is done is, so here, if I'm going to take the acid group, so it is unsaturated. So if I add iodine, Ki, sodium bicarbonate, and water, first thing what happens is lactones will be produced. So first, since you have added iodine, you're going to get here iodine, and here there will be hydrogen that is present. Now, in the presence of this particular reagent, you're going to get the I is replaced by H. So here double bond O. So here H and here also H. Right. So this is how unsaturated acids can be converted into the saturated lactones, and the aryl diazonium salts again can be reduced in non-aqueous medium with this particular reagent to aromatic hydrocarbons. So this also you can remember with respect to that of this particular reagent, that is tri-N-butyl tinide. Next, talking about osmium tetroxide, that is OSO4. So it is commonly known as osmic acid. It is an expensive and highly toxic reagent. Why it is used? It is used for syn hydroxylation of alkenes. So we have already come across this particular reagent when we were talking about the addition of two OH groups to the double bond in alkenes. So this reagent we have already seen, osmium tetroxide, right? So now applications of this particular compound. So first of all, hydroxylation, it proceeds through a cyclic osmate ester and vicinal diols are obtained. So this we have already seen what are the products that are formed. And again, this reaction is stereoselective and there is syn addition that is occurring, right? So let us see the example. Let us look at the example. So osmium tetroxide in the presence of pyridine. So we have, now what is going to happen? You're going to get, so here, for the double bond, the OH groups will be added. So you have OH and OH. There are also methyl groups that are present. So here we have methyl groups and here we have the methyl groups, right? So again, this particular reagent, as I already explained, it is stereoselective. And if you are taking strained and unhindered olefins or the alkenes, they react rapidly with osmium tetroxide. And the attack of the reagent is always from the less hindered side of the olefinic bond. So this also we have seen the example. So let us just take some other examples and look into this. So suppose we have this particular compound. You add osmium tetroxide. So the addition takes place so that here the OH and OH. So from the unhindered position, the OH groups are added. So here there is OH groups, which is this bond. You can see it is pointing towards us, right? So the attacks takes place from below, right? So this is how the attack is taking place from the unhindered side of the olefins. Okay. Now, when you're talking about the catalytic or osmium tetroxide along with hydrogen peroxide, if you use these together, the same result can be accomplished, but more economically by using this particular reagents together, osmium tetroxide and hydrogen peroxide. Then whenever the case is where more than one double bonds are present, then hydroxylation will occur at the most electron-rich double bond. So this also has to be kept in mind. So this comes under regioselectivity. So first of all, we know that osmium tetroxide, it adds OH groups to the double bond. Now, whenever there are multiple double bonds, then it goes for electron-rich double bond. So let us take an example. So here we have COO, CH3. Here COO, CH3, osmium tetroxide, water, acetone. Now, you can see there are two double bonds that are present. Now, here this is the electron-rich double bond, because here you have the C double bond O groups which are attached to this particular carbon, which will withdraw the electrons. So it is not electron rich. Here it is electron rich. This particular double bond is electron rich. So the OH addition occurs to this double bond, whereas this double bond remains as such unchanged. COOCH3, COOCH3. I hope it is clear how the addition takes place. Next, coming on to selenium dioxide SeO2. Even this reagent we have come across. So now let us look into, first of all, we know that it is a very good oxidizing agent. We have come across this particular reagent in this particular session itself, right? It is specific for alpha oxidation as well as allylic oxidation reactions, and it is toxic in nature and commonly used in dioxane, acetic acid, acetic anhydride, water or ethanol solvents. And it oxidizes ketones and aldehydes to 1,2 dicarbonyl compounds. And during oxidation, this particular reagent SeO2 is reduced to metallic selenium. Coming on to the applications of SeO2, it oxidizes alpha carbon of the carbonyl group. This we have already come across when we were studying about oxidation of carbonyl compounds. And this oxidation is possible when the alpha carbon, it should have at least one alpha hydrogen that has to be present. Okay, so methylene groups are more reactive when compared to that of the methyl groups. So this also we have seen. I've already told, right? This particular group is more reactive when compared to CH3. So I had given one example and I've explained. If there was CH2 instead of CH3, then how the oxidation would occur, right? So let us take example CH3, CH2, C double bond O, CH2, CH3 in the presence of this particular reagent, selenium dioxide. Now CH3, CH2. Now the alpha carbon, the alpha hydrogen will be oxidized, right? So we have CH2. Now we have, already there is a C double bond O. One more will be C double bond O and then CH3. So this is oxidized to C double bond O by SeO2. Next, again you can see this is more reactive CH2 group, and again it is alpha to the carbonyl group. So it is oxidized to C double bond O. Now again CH3, CH2, CO, CH3. In the presence of SeO2, we have CH3. Now there is only one, now there are two alpha carbons to the C double bond O group. Now we know that CH2 is more reactive when compared to CH3. So we know that the product should be C double bond O, C double bond O, CH3, right? If I'm talking about CH3, CHO. Now what you're going to get here, this is the alpha carbon. There is hydrogen that is present here. So you're going to get CHO, CHO. So this is how the selenium dioxide acts on the substrates to give the respective products. So mainly it is regioselective oxidation that is taking place, and mainly the alpha carbon has to be concentrated upon when we are writing the products. Right. So again, if you are looking into, suppose you are taking the compound like this, if there are CH3 groups. So here you can see there is no carbonyl group as such, but here you can see there is a CH3 group that is present. Now, this can be oxidized in the presence of SeO2. So you can get here the aldehyde group. Next, it is also a useful reagent for allylic oxidation of the alkenes. So if you are taking RCH, here CH3, SeO2. Now what happens is, this is the allylic carbon, right? This is the allylic carbon with respect to the double bond. So we have RCH, double bond CH. Now this will be oxidized to CH2OH. Similarly, RCH double bond CH2OH. Now this is the allylic carbon, right? So that will be oxidized. So alcohol will be oxidized to aldehyde. So we have RCH, CH, CHO. Next, talking about the other applications, it exhibits a useful stereoselectivity and especially in the reaction with tri-substituted gem dimethyl alkenes. So here the products are always predominantly the E-allylic alcohol that is obtained, okay? Especially when you're using the suitable substrates. And again, this is a stereoselective reaction. Now let us look into the reaction. So here we have CH2, CH3, H, CH3. Suppose you take this particular alkene in the presence of SeO2. So we have CH3, C double bond C, CH2, CH3. Now this CH3 will be oxidized to CH2OH, right? Now this H remains as such. Now again, this is the allylic carbon that is present. So allylic carbon, so this will be oxidized, and again the E-allylic alcohols are produced by this particular reaction. So because of which this particular product is more preferred. Okay, so that is why we have the CH2OH group that is attached here and not in this position. Next, it can also act as a dehydrogenating reagent. So suppose we have RCO, CH2, CH2, COR in the presence of SeO2, you get RCO, CH. Here, dehydrogenation takes place. So you get the double bond that is formed between these two. So one hydrogen from here, one hydrogen from here is removed. So you get a C to C double bond that is present, so because of which you get this particular product. Next, coming on to 1,3-dithiones. So these 1,3-dithiones can be prepared by the reaction of an aldehyde or its acetal with 1,3-propane dithiol. So how it is produced? So this is the method of preparation. And what is its main importance? It acts as a protected form of aldehydes as well as ketones, especially for protection. So whenever the aldehyde or ketone groups are susceptible to certain reagents, for protection of these groups, you can use this particular method of preparation in which 1,3-dithiones can be used for protection. So RCOH, so aldehyde. So we are going to treat it with 1,3-propane dithiol. So thiol has SH group, propane, so 3 carbon atoms, dithiol, so 2 SH groups on either side we have. Now BF3 and etherate. So now we are going to get the 1,3-dithiones. So here 3 carbon atoms already are there in the in this ring. So 2 sulfur atoms here. This is attached to carbon, that is carbon of the carbonyl group. So here we have R and one we have H. So this is 1,3-dithione. Talking about the applications of 1,3-dithiones, reaction of 1,3-dithione with N-butyl lithium, it forms a carbanion which can be easily alkylated. So let us look into it. So we have SS, here we have carbon, here we have R and we have H. So when you treat it with N-butyl lithium and PHX solvent, so we know that it can, this N-butyl lithium, it can easily abstract the proton. So one hydrogen is easily abstracted. So here R, this hydrogen is abstracted, so it becomes minus. So if you're treating it with any alkyl halide, now this R dash will come and attach here. So S and S, here R, and here we have R dash, right? So this is how the reaction proceeds. Now this 1,3-dithione obtained is a thioketal, right? And hence it can be hydrolyzed to aldehydes and ketones by treatment with the suitable reagents like HgCl2. So one of the reagent is mercury chloride. Now, in the sequence of reaction, the normal mode of reaction is reversed, right? So normally what happens, electrophilic carbon by conversion to 1,3-diethane is made to behave like a nucleophile. Usually the C double bond O, this particular carbon is electrophilic in nature. But now because of treating with 1,3-diethane, this particular carbon is from electrophilic carbon, it is converted into the nucleophilic carbon. So it is behaving as a nucleophile now. Right, you can see that easily here. The R dash is coming and attaching to this particular carbon. This particular carbon was electrophilic in nature. Now, because it is treated with the 1,3-diethane, it has become nucleophilic and the R dash comes and attaches there. So, you're going to change or reverse the polarity of the carbon, right? So, this reversal of polarity is called as unpolum. So, from the 1,3-diethane derivative of formaldehyde, you can prepare a wide variety of aldehydes and ketones. So, how do we do it? So, first take formaldehyde. Now treat it with the thiol, dithiol. So you're going to get, so propane, how we have prepared this 1,3-diethane, right? 1,3-propane dithiol we have used. So similarly, take this formaldehyde, treat it with 1,3-propane dithiol. You're going to get here 1,3-diethane. So here, yes, this is how we get. Now treat it with Rx. What you're going to get? Here, one of the hydrogen is replaced by R. So R here, and this remains as such. Correct? Now, if you're subjecting this to hydrolysis, you're going to get C double bond O. Here there is H and here there is R. Similarly, here if you are again treating it with R dash X, this also will be replaced by R dash and R. Here S. Yes. And again on hydrolysis, you're going to get R dash R C double bond O, right? So this is how ampulum can be induced, that is reversal of polarity can be induced in the carbonyl compounds by treating with the dithiol, that is 1,3-propane dithiol to form the 1,3-diethane, and then we can get the respective carbonyl compounds, right? Yes. Let us look into the other applications of 1,3-diethylenes. So with epoxides, if you're going to treat them, the anion of the 1,3-diethyl, it gives beta hydroxyaldehydes or beta hydroxy ketones. So let us look into this reaction. So here, suppose we have the R group, let me take it as a CH3. So the H can be removed by using a suitable base. So you take an epoxide. So here we have the epoxide. On hydrolysis, so this is the diethane part. So here what you're going to get, this is CH3, right? So here now the opening of the ring takes place. So CH2, CH, here there will be OH, and here there will be pH. Now this can give, you will get CH3, C double bond O, CH2, CHOH, and pH. So you can see here, this is the alpha carbon, this is a beta. So beta hydroxy aldehydes or ketones will be obtained by making use of this particular reaction. Next, it can also be used for the synthesis of alpha hydroxy carbonyl compound. So how do we do it? So here again diethane. So here if I take H and there is already, if one of the hydrogen is abstracted by a base, you take the carbonyl compound. Now we know that here again S, this will be joined here. There is a carbon that is present here. Now there is also H that is present here. Now this carbon can attach here. So you have OLi, PH and PH. So we have HgCl2, which is used for reduction, H2O, and CH3Cl. Now what you're going to get here, HCO. See, this is the carbon. So here there will be a double bond that is formed. So CHO, here we have this OLi will be converted to OH. Here we have PH and PH. So this is the alpha carbon, the alpha hydroxy aldehyde or ketone. So here they have since we have taken H here, you get alpha hydroxy aldehyde. Here if you would have taken R, you would have got the alpha hydroxy ketone as the product. Next, reaction with solid carbon dioxide followed by hydrolysis. It will lead to the formation of alpha keto acids when you're using 1,3-dithioanes. So again, let us write the equation. So here there is a carbon, here there is R. Let us write it as minus. So already there is one hydrogen that has been abstracted. Now carbon dioxide is C double bond O, C double bond O. Let us also subject it to hydrolysis, right? So again, sulfur, here also sulfur. Here we have carbon. So now this carbon of the carbon dioxide is attached now. C double bond O, and here it has OH, and here there is the R group that is attached. Now again the hydrolysis will take place. So you have C double bond O, here R, and then you have COOH, right? So here we have alpha keto. So this is the alpha keto group is present in the acid. So alpha keto acids are produced when the reaction with solids carbon dioxide is made with that of the 1,3-dithioanes. Right. Again, if you are taking the acyl halides, then with 1,3-dithione, they will give the dicarbonate compounds. So here we have 1,3-dithione. So here let me take one as R, and let us take one base has already been abstracted. So RCOCl, because we are talking about acyl halides now. This part comes and attaches here. So we have yes, and here R group, here there will be COR. So if I take it as R dash, here it will be COR dash. Now this on oxidative hydrolysis. Now what you're going to get, again this will break. So here you have R, C double bond O, C double bond O, R dash, which is nothing but dicarbonyl compound that is formed from the acyl halides. Right. Next, coming on to one of the important class of compounds, that is crown ethers. So these are large ring compounds. They are large cyclic polyethers which contain several oxygen atoms. And here they form stable complexes with the metal cations. So let us look into certain examples. So now suppose we have 4 oxygen atoms. These are joined together like this. Okay. So now we name it as, first you count how many atoms are present in the ring. Now, if I start from here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. There are 12 members in the ring. So we name this as 12 crown. How many oxygen atoms are there? 4. So 12 crown 4. Similarly, let us take some other examples. So here if I take, let me take 6 oxygen atoms. Now join together again. So here we have again the joining of the atoms. Now here let me also attach cyclohexyl rings, right? So now how do we name it as such? First count the number of atoms in the ring. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18, right? So it will be 18 crown. How many oxygen atoms are there? 6. But again, there are 2 cyclohexyl rings. So I write dicyclohexyl 18 crown 6, right? So similarly, you can also name it this as 1, 2, 3. If I take 5 oxygen atoms, again, if I join all the oxygens, now count the number of atoms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So 15 crown. How many oxygen atoms are there? 5. So 15 crown 5. Right. So this is with respect to the crown ethers. Now applications of this crown ethers. Dicyclohexyl 18 crown 6 complex with KMNO4, this particular complex, It is an efficient oxidant which is soluble in benzene. So this complex, again, it contains free permanganate ion. It is a very powerful oxidizing agent and it is used for oxidizing olefins, alcohols, aldehydes, as well as alkyl benzenes. So very strong oxidizing agent, that is the complex that is formed between that of the dicyclohexyl 18 crown 6 ether crown ether with KMNO4. So we have the example. So let us take this compound. So we have here. So here, let me take one more. Yes. Okay. Let me write it clearly. This is just the two methyl groups that are attached. Okay, like this. Yes. So now in the presence of KMNO4, and I'll just write the crown ether like this, 18 crown 6 and benzene, because it is a benzene soluble oxidizing agent. So I use benzene here. So you can see there is oxidation that is occurring in various groups, right? So opening of the ring takes place. So this remains as such. This particular group remains unchanged. This remains as such. Now here, this particular thing, here this carbon atom is oxidized to COOH. Next, suppose you're talking about the complexation of the cation of salts with 18 crown 6 ethers. It enhances the reactivity of its anions for nucleophilic substitution and also elimination reactions. So let us look into the examples. So C6H5, CH2Br on reaction with Kf. So here complexation takes place, complexation of the metal cation. So here K plus will complex with that of the 18 crown 6 in the acetonitrile. So here let me write acetonitrile. And I've taken the crown ether, that is 18 crown 6. So here what happens is you're going to get C6H5, CH2F. So this F minus can be incorporated into the substrate molecule. So you get KBr as the byproduct. So here there is substitution reaction that is occurring. Elimination reaction also can be facilitated. So before that, let us look into one more substitution reaction. So CH3, COCl. Again, if I take Kf is nothing but K plus F minus, right? So in the presence of crown ether, so we can get CH3, COF. Instead of Cl, there will be F, and this K will combine with the Cl. So you have KCl as the byproduct. So these both are the substitution reactions. So similarly, as I already told, elimination reactions can also be facilitated. So suppose we have cyclohexyl bromide in the presence of Kf and crown ether. So here the elimination reaction takes place. So this bromo group as well as one hydrogen will be removed off to give an alkene. So you get KBr plus HF. This is elimination reaction, right? And again, the crown ethers can be used for esterification reactions. Let us take the potassium salt of the carboxylic acid, and then here in the presence of crown ether, COCH2Cl. So here the Cl can easily be removed in the presence of 18 crown 6. So what is going to happen is this Cl and this K can combine together to form KCl. So KCl can be removed off. So we get Cl, benzene ring, C double bond O. Here we have CH2. Now this O, C double bond O, R will be attached here. So because of which you also get esters in the presence of 18 crown 6 or in general in the presence of crown ethers. Talking about metal hydrides, they are versatile reducing agents for selective reduction of functional groups. About this also we have studied, we have discussed much in detail in this particular video itself. So mainly they are classified into nucleophilic hydrides and electrophilic hydrides. Nucleophilic hydrides, they reduce polar multiple bonds, whereas electrophilic hydrides, they react with non-polar C double bond C or C triple bond C groups. Now, the most common hydrides that metal hydrides that we use for as reducing agents are lithium aluminium hydride and sodium borohydride, right? So lithium aluminium hydride, mainly it forms here Li plus and AlH4 mines, right? We have also seen how the mechanism is taking place when this lithium aluminium hydride is acting as a reducing agent. And this lithium aluminium hydride can also be represented as LaH. Some other reagents that can be easily derived from the metal hydrides are, let us look into these reagents. So first of all, we know lithium aluminium hydride, sodium borohydride. The other reagents are lithium tri-tertiary butoxy aluminum hydride, which is represented as LTBA. So how do we derive this? We take lithium aluminium hydride and treat it with, here we have the tertiary butanol that is taken in the presence of ether. We get lithium aluminium hydride, which is complexed with the, here this particular group. Along with that, there is hydrogen that is removed off. Along with that, we also have other reagents, that is lithium trimethoxy aluminum hydride, that is LiAlH4, treated with 3 moles of methanol. When 1 mole of lithium aluminium hydride is treated with 3 moles of methanol, we have lithium aluminium hydride with OCH3 thrice. There are 3 groups, this methoxy groups. There are 3 such groups attached to the this particular group. So we have again 3H2. So this is the, here this will be the cation and this will be the anion that is present in this particular compound. And dibal H we have already discussed, diisobutyl aluminum hydride, which is written as dibal H, right? So this also we know. So all these reagents have varying capacity for reduction, and again there may be difference with respect to the selectivity and the functional groups on which these particular reagents act upon. Now talking about the applications of metal hydrides, they act as hydride donors. So lithium aluminum hydride, it reduces aldehydes, ketones, acid chlorides, esters, carboxylic acids, and epoxides to alcohols. So directly all these compounds will be reduced to alcohols. Lithium aluminum hydride reduces nitriles, nitro compounds, and amides to amines. So all these groups will be reduced to amines when you're treating them with lithium aluminum hydride. Sodium borohydride, it is more selective when compared to that of the lithium aluminum hydride. It selectively reduces aldehydes, ketones, and acid chlorides. Now, when you're using a combination of sodium borohydride and lithium chloride, it reduces epoxides and esters. If you're using sodium borohydride and aluminum chloride, it reduces a wider range of functional groups except nitroalkenes and amides. So this is one slide which you need to remember very clearly whenever you're going to predict the products for the various reactions based on the questions that have been given. So you need to predict the products based on the reagents that have been given. So lithium aluminum hydride, it acts on a wide variety of functional groups, but it is less selective. Whereas sodium borohydride, it is much more selective when compared to that of the lithium aluminum hydride. We also have diborane as well as borane. So this also we have discussed much in detail about how the reaction goes about when you take borane as well as diborane and how the products are formed, right? So diborane is inert towards acid chlorides and nitroalkenes. And here these particular reducing agents, they reduce carboxylic acids, ketones, and epoxides. All these are reduced to alcohols. Nitriles are reduced to amines, alkenes into trialkyl boranes, and then hydroboration reaction. And of course, later it can be also used to prepare alcohols. Now, diborane, it is unreactive towards acid chloride and nitro compounds. Next, talking about LiR3BH, which is a more powerful reagent when compared to lithium borohydride because of the plus I effect of the R group and reduction in the solvation of the anion, right? So here, this with respect to this, because of the bulky nature, it is more reactive when compared to that of the lithium borohydride. And lithium borohydride as well as MgBH4 twice, these are also more powerful reducing agents than sodium borohydride, because again Li plus and Mg2 plus, they are more powerful complexing ions when compared to that of the Na plus ion. Next, lithium triisobutyl borohydride as well as the LTBA. So these are preferentially useful to give axial cyclohexanols, whereas lithium triisobutyl borohydride, it mainly proceeds the reaction by making use of this particular reagent. It proceeds by the thermodynamical control, whereas LTBA, when it is used, the reaction proceeds and the products are formed by making use of the kinetic control. So now, suppose you take this particular compound. So we have here double bond O and here a tertiary butyl group. Now, if you use LAH and if you can also use LTBA. So here there will be H and OH. Reduction is taking place. This remains as such. Here, this is a major, only I'm writing the major products. Okay, here again it will be the same. Here OH and H, right? So this is how, based on LTBA and LAH, there will be difference in the formation of products. The product overall will remain the same, but the kinetic and thermodynamic control plays an important role in this particular reaction, right? So based on how we are going to change the reagents that are used. Now talking about the borane, it is capable of reducing a variety of functional groups. So most important applications of the reagent, it is involved in the addition of the carbon-carbon multiple bonds, that is hydroboration. And I've already told it is mainly used in the preparation of alcohols. You can use this borane. So let us write the reaction about the hydroboration reaction. So CH double bond CH2. So here we have BH2. So this bond, it can shift here and this attacks here because this is electron rich. So it attacks the boron and here the bond shifts here so that the H will attach to the carbon. So we have RCH. Here the H is going to attach to this carbon. Now this bond slowly breaks and here it is CH2 and this bond is present. So now what happens? This is the intermediate that is present. Now we have RCH2, CH2, PH2. So this is hydroboration reaction. Now when we are talking about the bulky boranes, dialkyl boranes, NBBN, right? Along with that SiA2B. So I've also written here bulky boranes. That is, one example is NBBN and SiA2BH. So this we have already come across in this particular video itself. So these are commonly used and these two reagents are used in those cases where the hydroboration is required. And dialkyl boranes, though they are less reactive, they are more selective reagents than the borane itself. Now NBBN is nothing but we have, so this is the structure of NBBN. BH, this is NBBN. So bulky boranes. So again, if you're talking about dicyamyl borane, this we have already come across this particular reagent. So CH3, here CH, CH, so cyamyl group. So this is SiA2BH, right? So these bulky boranes can be used so in cases where hydroboration is required, and these are more selective reagents when compared to that of the normal boranes which you are using, right? So this is about the diboranes as the reducing agents. So now if I am taking an example, so here double bond O. So this is less hindered here, less hindered region. So if I'm taking the R2BH, that is dialkyl disubstituted boranes. So if I take the R2BH as, let us say, R2BH. Let me take it as 9VBN. So here what you're going to get, the alkylation has to take place, right? So here OBr2, and here you have H, and here there will be the alkyl group that is attached. This on hydrolysis, you're going to get here OH, here H, and here there will be CH3 group. So this is mainly applicable when we are taking bulky boranes that are present, and these are more selective comparatively, right? So because of more selective nature of these bulky boranes, mainly the attack takes place in the less hindered side so that you get the required product.
The continuation of this topic will be done in part 2 of the video. The part 2 will contain detailed explanation on catalysts, stereoselective, regioselective and chemoselective reactions, along with which I'll be explaining about 3 important reactions in detail, that is Shapiro reaction, Chichibabin reaction and stock-enamine reaction. I hope the video is useful. Thank you so much for watching the video. Subscribe my channel for more such informative chemistry related videos. Thank you.